on the side as well. Okay, are we ready to go then? You got the mic and everything ready to go? Okay, welcome everybody. It's my great pleasure to introduce today's speaker, Maria Madsen. Maria is a native of La Crosse and has been a student at the University of Wisconsin-Madison since her freshman fall 10 years ago. When she first arrived on campus, she was afflicted with the desire to pursue an undergraduate degree in physics. But that changed when she learned how comparatively youthful our own field is. In fact, she was particularly taken by the notion that the first operational forecasts were not even 60 years old at the time when she was a freshman. Looking back through my own email, I found that my first contact with Maria came on a gloomy February day in 2012, when as a student in my AOS 101, who wasn't able to make my regular office hours, she requested a time on the alternative schedule to come and introduce herself in person. So she took a National Weather Service internship in her hometown in the summer of 13, and she started that fall working with Greg Tripoli in research because she finished her math and physics degrees requirements early. And then she also took AOS 452, which is a class I like to teach in the fall, in that same fall of 2013. And I remember thinking Maria's individual research project was really good. And so I was immediately interested in recruiting her as a graduate student. And with some last minute budget juggling, I was able to get her to join my group, and she began in the fall of 2015. Now, for those of you who don't know Maria, and it's a great misfortune if you don't, she's a very interesting and multi-dimensional person. She's been an exceptional teaching assistant in a number of assignments for me and others. She can seem quiet and docile, but that demeanor hides a stiletto sharp sense of humor, which gives as well as it takes. Her favorite target is my handwriting, which she will attack at every opportunity she gets to criticize it. And I figure that's fair because I get to criticize her writing all the time. She's a lover of dogs. She's an evangelist for kombucha, but trying many times unsuccessfully to convince me of the wisdom of imbibing tea fungus despite the gag-inducing taste. She's also the only person I know who rides a unicycle. And that's not a small matter, because riding a unicycle surely familiarized Maria with scrapes, bruises, and other associated physical discouragements, all of which are relatives of the obstacles one encounters on the road to a Ph.D. So it seems to me that only a person of special constitution, and that's how I'll always think about Maria, can summon the wherewithal to meet either of those challenges. Maria has been expanding our knowledge of the intraseasonal variability of the wintertime Pacific jet stream over the last 6 years, and especially in the last 2 COVID years, has accelerated that progress and really thusly consolidated a hard-won expertise that she now wields as a nearly completed Ph.D. With the help of her committee members, Maria has certainly led me to places I would never have gone on my own, and she's done it really well. So pending a successful outcome today, Maria will be headed to the Karlsruhe Institute of Technology in Germany to begin a postdoctoral appointment under the guidance of Professor Christian Grams. So, as is always the case, I'm excited about her future, but I am sad to see you go, Maria. And so, Maria Madsen will discuss elements of her Ph.D. research on characterizing the intraseasonal variability of the wintertime Pacific jet. And I'll turn the slide off.
Thank you, John. Can everyone hear me in the back okay? All right, awesome. Well, thank you for that great introduction. And I just want to say again, I know John said, that one of the first draws for me to the atmospheric science that drew me away from just physics and math was learning just how new this science was. And along with learning about the operational forecast models, I remember sitting in the 100 class as a freshman and learning that the jet stream in particular wasn't even common knowledge, and we didn't really know a lot about it till well after World War II. And this fact kind of blew my mind. And then over the next 4 years of undergrad and 6 years of grad school, as I learned more and more about the jet stream, it became harder for me to wrap my mind around the fact that my grandparents, and even my parents when they were younger, grew up in a time where we really didn't know a lot about the jet stream. And this is surprising to me because, as many of you might already know, and maybe some of you don't, the jet is responsible for more than just your flight time from one coast to another. It also largely impacts the day-to-day weather that we see and longer-term climate. So over the last 6 years, I focused on the Pacific Jet, the North Pacific Jet, or this region here. And I just have shown here just like a 20-day or 18-day animation forecast of the jet. And we can see its upper level wind speeds, and over the course of the 20 days, you can see it's quite variable. It seems to be anchored over the East Asian coast here, and then over this 20 days, you can see it fluctuates poleward or equatorward, it breaks off and goes over the United States, and it's just quite variable over this time. So I've been focusing on characterizing this variability a little bit more, and specifically the transitions of the wintertime Pacific jet stream. So for today, I want to provide you a little bit more of a background, including where we're at currently with the North Pacific jet variability knowledge, and then go into some of the research objectives. And then next, I'd like to focus a little bit more on the North Pacific jet variability, including some of the new methods I've applied to characterize it, and then looking at some teleconnections associated with these. And then next, I'd like to go into characterizing these North Pacific jet transitions as preferred or likely and unlikely at varying time scales. And for today, I'm just going to focus on the time scales of 10 to 20 days. And then I'll talk about the predictability of these transitions through the lens of a linear inverse model. And then I'll just conclude with some takeaways from what I've shown you today. So our current understanding of the intraseasonal variability of the North Pacific jet is centered on these two predominant patterns. The first is a zonal extension or retraction. So here we just have the 40 meter per second climatological jet in gray, and we can see that this leading pattern is an extension or a retraction with these anomalies here. And then the next leading mode is around a 20-degree meridional shift of the jet exit region here with anomalies poleward and equatorward. Now these leading patterns are associated with basin scale anomalies in the Pacific that have substantial impact on the synoptic scale structure and downstream sensible weather. So for example, Chu et al. In 1993 demonstrated that the zonal extent of the Pacific jet had a considerable impact on the Hawaiian wintertime rainfall. So they analyzed two consecutive winters between 1981 and 1983 and found that a zonally retracted jet was associated with a significantly wet winter in Hawaii, whereas the extended jet was associated with an extremely dry winter. Additionally, in constructing a climatology of subtropical cyclones over Hawaii, Akin and Martin in 2004 found that a retracted Pacific jet is linked to an increased frequency of the storms in the Central Pacific. So similarly, Jaffe et al. In 2011 examined 19 cold season jet retraction events and found that the variability within the Pacific storm track occurs in tandem with these retraction events. So here we can see that there's enhanced storm track density downstream and poleward prior to the retraction. So this is denoted in the dark gray dots here. And then after the retraction, you see there's a dashed gray 40 meter per second isopath. We have an enhanced storm track density and more centered in the Central Pacific. So these retraction events were also associated with the rapid onset of a PNA pattern, and they found to be around 10 days. And they were also associated with a shift from a negative to positive anomaly in 500 hectopascal geopotential height and sea level pressure. Breeden and Martin in 2019 looked at a specific retraction that was long-lived in February 2006, and they found that nonlinear interactions largely influenced the onset of this retraction. So in addition to sensible weather impacts over Hawaii and elsewhere in the Pacific Basin, other recent studies have demonstrated that these leading patterns of the Pacific jet have impacts over North America as well. So Griffin and Martin in 2017 showed that these jet extensions, you can see as extended here, are associated with warm anomalies around 850 hectopascal localized over western North America. Now, if you compare this to a retracted jet, we can see that these warm, low-level anomalies there's cold anomalies over the western North America associated with the retracted jet. And if we look at a polar deflected jet, these are associated with warm anomalies over central Canada. And then compared to an equator deflected jet, we have expanded cold anomalies over most of Canada here. So even more recent work by Winters et al. In 2019 has shown that the mode or the pattern of the North Pacific jet has a really big impact on the medium range forecast skill. So this study, they analyzed 30 years of global ensemble forecast system reforecast and found that the greatest forecast skill was verified during an extended or polar deflected jet, whereas the worst forecast skill was verified during a retracted or an equator shifted jet. Additionally, there was reduced forecast skill when forecast periods occurred during this transition between these patterns. So despite this recent work demonstrating that the Pacific jet variability has a substantial impact on the large-scale structure and sensible weather, and even forecast skill in and around the North Pacific Basin and over North America, these transitions of the Pacific jet are still poorly understood. So this led to 3 kind of groupings of research questions for my Ph.D. work. The first is, are there preferred transitions within the wintertime Pacific jet? And if so, what are they? The next is, what is the characteristic evolution, synoptic scale structure, and downstream impacts associated with the preferred transitions? And then as a third grouping, how predictable are these transitions? What is the role and relative importance of tropical heating and the extratropical circulation on these transitions? Now, because it's impossible to fit 6 years of work into an hour talk, I'll just be focusing on aspects of the first and third research questions here. So to do so, I employed daily 250 hectopascal zonal winds from NCEP-NCAR reanalysis over 71 cold seasons, and I defined a cold season as November 1st through March 31st, all the way back to 1948-49, to the 2018-2019 cold season. I first apply empirical orthogonal analysis, and then I apply a new method for characterizing variability in the self-organizing maps to find patterns of wintertime Pacific jet and look at these transitions on shorter and longer time scales. And I do this with transition probability tables all the way from short as 5 days to as long as 20 days. And then lastly, which we'll go into further, I apply a linear inverse model to look at the predictability. So previous research on jet variability has relied heavily on something called empirical orthogonal function analysis. And this has been very useful. However, the leading patterns only explain about 30% or less of the total variance, and these modes or patterns are linearly independent from one another. So although EOF analysis has been really important for developing and understanding Pacific jet variability, it kind of provides a static view of these Pacific jet transitions. So my work, I applied something called self-organizing maps, which I'm just going to call SOMs from here on out. Now, SOMs is a method within the field of artificial neural networks, and it organizes large, multi-dimensional data sets into finite arrays of recurring physical patterns. So this method has been gaining popularity over the last few decades, and it's been applied to a wide range of atmospheric or oceanic phenomena, both for feature extraction and classification. So the SOMs is trained through an unsupervised iterative process, and it begins with a grid of generalized patterns. So you can think of these as generalized patterns. These are just defined by reference vectors, and then nodes within close spatial proximity to one another are just considered, referred to as neighboring nodes. So a training period ensues in which the input vectors of the daily, I use the daily 250 hectopascal zonal winds, they're read into the SOM, and then they're matched to the reference vector here of the greatest similarity, and this can be measured by Euclidean distance between the input and reference vector. And then a self-learning process continues, and it updates both the node that it became, and then also it updates the properties of the neighboring nodes so that it maximizes differences between the input and neighboring nodes. So for my work, I use a 3x4 SOM grid. It consists of 12 different patterns, or I'm going to refer to them as nodes. And I did this because smaller grid sizes just led to a blending of what I consider relevant patterns, and then larger grid sizes yielded some not easily distinguishable patterns from one another. So I just wanted to show you the EOF, the empirical orthogonal function analysis of this extended cold season. And we can see once again, we have the leading EOF is a zonal extension or retraction of that jet exit region, whereas the next is a poleward or equatorward deflection of the jet exit region. Now these are the 12 SOM nodes, and once again we have our 40 meter per second climatological isotap. And we can see that with the 12 SOM nodes, we have nodes that kind of look like those leading EOFs, and then we have different variations of them. So on the left-hand side here, we have different types of, we could call a jet retraction, where it's nearly along the jet exit region, or for SOM 1, it's a little bit equatorward of that. Whereas on the right-hand side, we have different types of jet extensions at different latitudes. So nearly along that jet exit region, slightly poleward for SOM 4, and slightly equatorward for SOM 12. And then along the top, we have different variations of a poleward deflection of the jet exit region. And near the bottom of the SOM grid, we have nodes that feature some equatorward deflections. And then in the center here, we have anomaly states that are quite weak. So we only have like 8 meter per second anomaly for SOM 6 in the jet exit region. And then SOM 7, it looks like a kind of enhancement of that jet exit region. And then you'll notice below each node here is an associated frequency of occurrence. And this is just the number of days that characterize each SOM node. So we have the highest frequency of occurrence in these weaker anomaly states, and some of the lowest frequency of occurrence for the really strong extensions denoted by node 12. Now we can actually look at the relationship between the two leading EOF or PC patterns of a North Pacific jet and these SOM patterns by using the days that characterize each of these SOM nodes and projecting them onto the EOF two-dimensional phase space. So we can think of it, the two dimensions, the x-axis would be your extension on the positive, retraction on the negative, and your y-axis would be a polar deflection and equatorward deflection of the negative y. And if we project all those days that characterize each of the SOM nodes, we can see clear clustering in specific quadrants of the phase space that are quite consistent with what we saw in the pattern, where we have different types of retractions on the left-hand side, with node 5 looking most like that canonical retraction, whereas different clusterings of an extension are noted on the right-hand side of the SOM space, and then poleward deflections on the top, equatorward deflections, and then 6 and 7 are within that one unit circle here and denote kind of weaker anomaly states. But we do still have, despite these consistencies within the leading EOF modes of Pacific jet variability and many of the SOM nodes, there is still scatter evident in the phase space. And this suggests that the subtleties of Pacific jet variability are just rather represented by our SOMs in the traditional EOF PC phase space.
I have a question. So
Sure.
how do you decide that two maps are close together? Like what's the metric that's used in creating the self-organizing maps?
Yeah, you can also look at kind of it's called a salmon map that looks at the Euclid or the distance between each SOM node, which I don't have here, but it'll show like which nodes are actually most similar to one another.
I guess I'm just asking, is it like root mean square
Oh,
error?
but
Like,
yeah, it's
what's
root mean
this-
square error. Yeah,
Okay.
that's how you determine it.
Okay.
Yeah. All right, so you can also look at your mean residence time, so how many days a particular day will stay in that node. And we can see that the mean residence times reflect kind of this transient nature of the jet stream, with a range between 2.2 days to all the way to 4 days for node 12, which was that extension. However, if we compare this to the maximum number of consecutive days residing in a particular node, this ranges between 10 days for nodes 3 and 7 to 44 days for that extension denoted by node 12. So this stark difference between mean residence time and max residence time kind of highlights the complex nature of the jet stream variability, in that while short fluctuations of the jet stream are common, the jet can also exhibit this weekly to monthly persistence. And then also, we can look at something called the quantization error, which is similar to that root mean square error for each SOM node, which provides a measure of error between the days characterizing the node and the anomaly pattern depicted in the prior figure. So smaller mean QE just means a pattern that's better representative of the days characterizing the respective nodes. So we can see that there's larger QE values that feature equator deflections or jet retractions, whereas lower QE values are associated with polar deflected nodes 2 and 3. I also look at the frequency of occurrence for each SOM node over each cold season, all the way back from 1948 to 2018. And this reveals substantial interannual variability, where we can see abrupt year-to-year changes with many of the nodes here. And then one way that I look at the interannual variability between nodes, you can calculate the variance within each time series. So node 3 had some of the smallest variances, about 18.9, whereas node 6 was also quite small, with a variance of 19.5. The regimes with larger variances were nodes 2, and then specifically also node 12, which had a variance of 68.2. And I want to draw attention to node 12 as well, because along with having a considerably large variance than the other 12 nodes, the extension denoted by node 12 also had the largest peak in the time series, which was an annual cold frequency of 43% in 1982 and 1983. Now this cold season was also characterized by one of the strongest El Nino events on record. And so this is kind of unsurprising because prior work has shown that the increased sea surface temperatures over the central and eastern Pacific, in tandem with their anomalous convection associated with El Nino, provides a favorable environment for jet extensions. The strong El Nino seasons of 1957 and 1958 and 1997 to 1998 are also characterized by peaks in the SOM node frequency of occurrence. In fact, there's actually a 0.58 correlation between the node 12 time series and then the Nino 3.4 index. And this is the highest of any of the other SOM nodes. So as demonstrated by this figure and other studies too, large-scale atmospheric teleconnection patterns are related to fluctuations within the Pacific jet and are likely tied to the interseasonal and intraseasonal variations and frequency distributions of these nodes. So I actually look at the relationship between some of the atmospheric teleconnections, including the Pacific North American teleconnection pattern, the Arctic Oscillation, ENSO events, and also the Madden Julian oscillation. So we'll just start with the Pacific North American teleconnection, or the PNA. And this is a dominant wave-like teleconnection pattern in the North Pacific, or the Northern Hemisphere, and it drives temperature and precipitation anomalies in North America, and is associated with fluctuations of the Pacific jet. So in its positive phase, you have an anomalous trough over the North Pacific in southeastern U.S., and then you have anomalous ridges over the subtropical North Pacific and the intermountain west of North America. So I look at this by using the daily PNA index values that are standardized, and then I separate between positive PNA events, negative PNA events, and neutral PNA events, where the positives are an index above 1, negative index below -1, and the neutral is between minus and +1. And we can see that positive PNA events are largely associated with the jet extension. The peaks in node 8, which is the highest here, 30% almost, and then followed by node 4, which was an extended regime, and then also node 12 here. And if we compare this to negative PNA events, these are associated with larger frequency of occurrence of node 5, which was a retraction, and then also node 9, and then a retracted / equator deflected jet denoted by node 10 here. Now another dominant northern hemisphere teleconnection pattern is the Arctic Oscillation. So during a positive Arctic oscillation, you have anomalously low pressure over the Arctic, and then you have anomalously high pressure over the North Pacific and North Atlantic basins. And then the negative phase is just characterized by a pattern nearly opposite of that. So similarly to the PNA, I utilize standardized AO indices here, and I use positive, I look at positive AO events, negative, and neutral. And we can see that during positive AO events, we have larger frequencies of occurrence of node retractions denoted by node 5 and 9, whereas the negative ones we have higher frequency of occurrence of these more extended nodes or / enhanced nodes, which is node 7 here. But we notice that these discrepancies between positive and negative AO events are not nearly as large as when for the PNA. And then I also wanted to look at the El Nino Southern Oscillation, or ENSO. And we saw evidence of a correlation between node 12 and ENSO. And this relationship is examined a little bit further by applying a similar method here and using Nino 3.4 standardized indices, where a positive ENSO is above 1, a negative ENSO is below -1, and then we have a neutral ENSO between -1 and 1. And we can see that the positive ENSO events have peaks in node 12 here, the largest one, and then node 8, whereas negative ENSO events all have larger frequencies of occurrence of nodes that feature some sort of polar deflection. So along the top edge of that sound grid. All right, so I also want to look at another important teleconnection pattern that's tied to changes of the North Pacific jet, and that's the Madden-Julian oscillation, or the MJO. Now this is the leading mode of tropical intraseasonal variability, and it's characterized by anomalous tropical convection that migrates east over time periods of 30 to 60 days. And it's typically characterized by 8 phases. So during the earlier phases of the MJO, we have anomalous convection in the Indian Ocean, and then as we move to the middle and later phases, as convection migrates east, where by the later phases we have anomalous convection then in the East Pacific and suppressed convection over the Indian Ocean. Now these phases have been tied to changes of the Pacific jet. So an example of this is from Moore et al. In 2010, who found that phase 3, where you had suppressed convection over the Pacific and enhanced convection over the Indian Ocean, was associated with the retracted jet with negative anomalies here. And then later phases were associated with an extended jet. So I look at the influence of the MJO on the 12 SOM jet states through calculating a % change in anomalous frequency of occurrence of the 12 nodes following strong MJO phases. So this % change is calculated at lags of 1 to 16 days following strong MJO phases. And then I identify a strong MJO phase or strong MJO events using the real-time multivariate RMM index from November 1st to March 31st, 1974 to 2019. And then the indices consist of RMM1 and RMM2, which are just defined by the leading 2 EOS of satellite-derived or satellite-observed outgoing long-wave radiation anomalies, and then the upper and lower level zonal link anomalies. And then our MJO amplitude, I consider events greater than 1, where our MJO amplitude is just defined by the RMM1 squared plus RMM2 squared, the square root of that. So in comparing SOM nodes during different MJO phases, an existence of statistically significant anomalous occurrences and also a slope as a function of lag can indicate an MJO forcing. So along the top here I have our SOM nodes, and then I have below them the associated, like the normal frequency of occurrence that we see. And then on the right-hand side here is the different active MJO phases. And then we have the lags from 2 to 16 days on here. So the orange bars just indicate statistically significant enhanced frequencies, and then the green bars indicate statistically significant reduced frequencies. So we're looking at the earlier MJO phases where we had our enhanced convection over the Indian Ocean. The retraction denoted by node 9 here has some of the largest increases in anomalous frequency. It is approaching 200% almost in the week following the active MJO phase 1. But if we move on to MJO phase 2 and 3, we can see that the retraction then characterized by node 5 has some of the largest peaks here. And then whereas node 9 here by phase 2, it goes from an increase in the week, in the first week with phase 2 to a decrease after 10 days. Now, extended nodes 8 and 12 here we can see have statistically significant reduced anomalous frequencies and almost approaching at 0% in the week following phase 3 here. So during the middle phases of the MJO, where our anomalous convection is starting to migrate east, nodes 5 and 9 start to exhibit reduced frequencies and anomalous occurrence. And then we see that the extension denoted by node 12 starts to have enhanced frequencies. And this anomalous frequencies approach 200% in the week after MJO phase 5. And then I just want to compare this to SOM 8, which is another extension here. And we can see that although they both feature extension, kind of this equatorward extension seems to be more associated with this MJO. And then if we look at the later phases of the MJO, we can see once again, MJO phases, SOM nodes 12, some of the largest increases here, and then by the later phases, SOM node 9 here begins to increase in frequency of occurrence. So overall, the nodes that are most strongly tied to the progression of the MJO during these active MJO events are nodes 5, 9, and 12. So I just want to summarize some of these earlier findings here. So I use a self-organizing map analysis that expands and complements the previous EOF analysis, and I identified 12 Pacific jet patterns that resemble variations of this extended retractor regime and poleward equator deflected patterns, but also new and more a little bit complex modes of variability that weren't captured just by EOF analysis. And we saw that there's substantial interannual variability of SOM node frequency of occurrence. And this was evidenced to be at least in part tied to teleconnection patterns like the PNA, AO, ENSO, and MJO. And node 12 specifically has one of the strongest relationships to these teleconnection patterns. But if we compare, if we saw like 12 to 8 or nodes 5 and 9, you can see that what seems like similar Pacific jet patterns, they might actually be driven by different extratropical or tropical processes. So although these teleconnection patterns provide insight into the varying nature of SOM nodes at inter and intraseasonal timescales, a key objective of my work was to see if there are likely and unlikely transitions between the wintertime Pacific jet. So once again, I just wanted to see, if you start in SOM 1, what is the likelihood that 5 days, 10 days, 15, or 20 days later, you'll transition into any one of these SOM nodes. So to do so, I calculate transition probabilities between these SOM nodes at varying timescales from 5 days all the way to 20 days to look at differences between these rapid transitions to longer 2 to 3 weeks. And I do this based off of a first-order Markov chain in which the probability of transitioning to any SOM node J at leg N, it just only depends on your initial node I. So here I just want to show you a few of these transition probability tables. You have the original node on the left-hand side, so where it begins, and then the final nodes on the top here. And then leg 10 is just denoting this 10-day transition probability. So red boxes denote statistically significant enhanced transitions, and then blue boxes indicate statistically significant reduced probabilities. So just as an example for this first one, if you're starting in node 1, there's a 17% likelihood that after 10 days you'll still be in node 1. A 9% likelihood you'll be in node 2, 8%, and so on. So we can see that at 10 days, persistence is likely for most of the nodes, and we can see this along the diagonal here. And in node 12 here, that extension has some of the largest persistence, 20%. Our preferred transitions we can see is off-diagonal points here. So we can see that there's preferred transitions from node 2 to 1, 5 to 9, 9 to 10, 10 to 9, 11 to 12, and then 12 to 7. And then just to get a visual here of these preferred transitions, here's our song grid, and then the red box just indicates an enhanced likelihood to persist, and then our red arrows show where our preferred transition is into. And we can see that of these preferred transitions, many of them are in the bottom half here, featuring from a retraction to this extended state. And then we also see that not a lot of preferred transitions. There aren't really any into these weaker anomaly states here. And then I also wanted to look at now 15 days, so beyond 2 weeks here. We see that persistence is only likely for node 12, so the persistence signature is dropped off for most of the other nodes. And then our preferred transitions are from nodes 2 to 1 or 3, 4 to 2, 10 to 5 or 9, and then we still have that preferred transitions from 11 to 12. And then here's just a graphical figure of those preferred transitions. And I also want to draw your attention to the fact that at 10 days and 15 days, we don't see any preferred transitions from one area of the song grid to a nearly opposite. But then by the time you get to 20 days, you still have a persistence for node 12, and then your preferred transitions are from 3 to 1, 4 to 3. You still have a preferred transition from 11 to 12. And then the one I want to draw your attention to is the preferred transition from 9 to 8. So this is actually a transition from a retraction here to an extended state. And what's interesting is that we don't see any preferred transitions from these extended states to the retracted states, kind of showing this asymmetry in the preferred transitions. So just looking at these preferred transitions, they're not random. So at short to medium 5 and 10 day transition times, almost every node has a likelihood to persist. And then most of the preferred transitions at 10 day occur into nodes featuring equator deflections. And we had substantial anomaly shifts that were not evident until longer time scales. So at 20 days, we saw that transition from a retracted jet into an extended. And I just want to say I've also calculated these probability tables over a shorter cold season, just from December to February. And this preferred transition it was actually occurred at 15 days as well, and from 15 to 20 days. So, and the opposite was not observed either, where you went from an extended state to a retracted. And I also want to draw attention to the unlikely transition. So nodes depicting these robust jet extensions had at least one reduced likelihood of transitioning into or from a retracted jet. So these more commonly studied transitions from an extended to a retracted jet are rare compared to other transitions. So now I'd like to move into an aspect of my third research objective, which was how predictable are these transitions? And I look at this predictability through the lens of a linear inverse model. Now the LIM, I'm going to call it LIM for short. This is an empirical model wherein the coarse-grained system dynamics are estimated as the sum of slowly evolving linear dynamics and then also rapidly evolving stochastic white noise. So recent research has found that has used the linear inverse model successfully, both to quantify optimal precursors of patterns over the North Pacific and North American region, and also as a forecast tool with comparable intraseasonal forecasts to operational models. The LIM is both computationally inexpensive and it's also really versatile in its application. So it makes it an ideal tool to look at these specific jet transitions. So as I mentioned, the linear inverse model assumes a linear approximation to the full system. So the system X is characterized by this linear stochastic equation, where L is our dynamical system matrix that represents the linear approximation of the system dynamics. And then this rapidly decorrelating nonlinear remainder is approximated by the state-independent but observationally constrained Gaussian white noise. So in this work, the forecast operator L is constructed of ERA interim 5-day running mean anomalies of 250 hectopascal zonal wind, apparent heat source Q1, 200 hectopascal stream function, and 800 hectopascal stream function. And for each of these, I use EUF truncated. So I have 8 EUFs, 15, 13, and 11. And the truncations for each field is just selected to retain a numerically stable limb. And so my final X has 46 total EUF components. So the homogeneous component of this equation can be solved with the propagator G tau here to obtain some deterministic evolution from a time at 0 to some leg of your choosing. So this propagator G is just your leg covariance statistics of the system. So we can use a linear inverse model and run it forward as a forecast model, where forecasts for X can be determined for any leg that you choose just by recalculating G. We could also run the limb in kind of a climate mode. So you can run it as a climate mode, which I just call a forward noise integration model. And this is what I use to generate synthetic specific jet transitions and this time-dependent empirical dynamical model. And I do this just through integrating the equation in just a two-step process using a finite time step. So with this forward integration model or climate mode of the limb, I use this to look at whether these preferred and unlikely transitions that we observed in the reanalysis can be reproduced in a linear inverse model and give us an idea of which of these preferred transitions are driven largely by linear processes. So I run this climate model forward for 10,000 days with a time step of 3 hours to get 10,000 simulated Pacific jet patterns. And then because I'm interested in looking if I can reproduce these SOM transitions, I have to kind of recreate my SOM grid in this limb space. So how I do so is I take any, from that simulated time series, I have a Pacific jet pattern on some day of that time series. And then I'm just looking at root mean squared error difference between each of these patterns that have been projected into the limb space and this pattern here. And then just whichever one has the smallest root mean squared error, which in this case would be 3. And this node now is considered SOM node 3, which is just the new limb-derived SOM node. And so for those 10,000 synthetic data Pacific jet patterns, we now have 10,000 SOM nodes. And I can composite all of those SOM nodes and look at the comparison between that and our actual reanalysis grid. And we can see that these look very similar to our reanalysis, where we have retractions on the left-hand side, different extensions on the right, polar deflections on the top grid, and equator deflections near the bottom here. A big difference is in the middle of the grid here, which in the reanalysis we saw that these were kind of weak anomaly states. But in the limb here, we can see these anomalies are quite a bit stronger. And they also have a lower frequency of occurrence. And then other differences in frequency of occurrence, SOM node 12 occurs more frequently in the limb than it does in the reanalysis, which is about 6% in reanalysis and 10% here. Otherwise, the other nodes had only like a 1 to 2% difference in frequency. So I can use these new limb-derived SOM nodes to calculate those same transition probability tables. And I just wanted to show you a few of them here. So here's the transition probability at leg 10 for the limb nodes, and then once again we have the original node on the left, the final node on the top here, and then we can see that our statistically significant enhanced transitions are, a lot of them are just on the diagonals here indicating this preferred persistence for many of them. if we compare this to the reanalysis, we can see then that the persistence of all of the nodes from the reanalysis are also recreated in the limb, except the limb also has preferred persistence for nodes 6 and 7 and 5, whereas it's not the case for the reanalysis. And then consistencies in actual preferred transitions, there's very few consistencies at 10 days. I didn't show you 5 days, but there are more at 5 days, much more at 5 days than there are at 10. But some of the preferred, the transition from 11 to 12, which is 18% in the limb and 20% in the reanalysis. And then we also have the transition from 2 to 1 that's identified in both. By 15 days here, we can see that many of the statistically significant preferred and unlikely transitions have dropped off here. We still have much more persistence than in the reanalysis data set here. But of these persistence, node 12 is likely to persist both in the limb and reanalysis. And then preferred transitions, there are no preferred transitions that are likely in both the limb and the reanalysis here. So the probability tables that were constructed from these limb SOM node time series revealed that at 5 days, many of the preferred and unlikely transitions were consistent, but when you get to 10 days and beyond, only a handful of the transitions remain consistent or persistent. Yeah, so this was mostly the persistence that was correctly identified for many of the SOM nodes at 10 days. And specifically, node 12 had the highest persistent likelihood in both the limb and observation. Whereas the only consistent preferred transitions into other nodes were from the retraction node 9 to 10 and equator were deflected node 11 to 12. But beyond 2 weeks, only the likely persistence of node 12 was captured in these limb probability tables. And then the lack of consistency between the limb-derived SOM transitions and reanalysis beyond 10 days could indicate either that these observed preferred transitions are driven largely by nonlinear processes that just can't be modeled by stochastic white noise, or maybe just that my state vector that is used to construct the limb has an insufficient number of variables. So I could include something on the surface like sea level pressure, or perhaps something near the tropopause to help model these transitions better. And then I didn't get a chance to show you here, but I also looked at, because node 12 had some of the most consistency between the limb and the reanalysis, I looked at optimal precursors for node 12 in the limb. So just some takeaways I want to wrap up here. The new method applied to characterize wintertime North Pacific jet variability using SNOMS expands on previous EOF identified leading modes. So this provides a more detailed assessment of the nature of jet stream variability. These differences in associated teleconnections and preferred and unlikely transitions between the 12 SOM nodes suggest that these important jet structures in distinct underlying processes and teleconnections may have been unknowingly merged with previous just EOF analysis. And then we see that preferred transitions are identifiable from short 5-day legs all the way to 20-day legs. But at timescales beyond 2 weeks, you see this extension this retraction likely to extend. And then this occurs on shorter timescales over just a DJF period. And then most of the preferred transitions beyond 10 days are not well modeled by the limb. But as I mentioned before, these likely and unlikely transitions that involve the extended node 12 seem to be best reproduced by the limb. And this could be tied to the fact that the limb had some of the strongest association with teleconnection patterns like ENSO and the MJO. So with that, I would just like to acknowledge so many people, which I cannot even fit everyone on this slide here. The fact that I've been here for 6 years means I have a ton of people to thank. First and foremost, I'd like to thank my advisor, John. You've been so supportive for me from day one, and I know I wouldn't be here without you, so I really appreciate everything you've done. And then the rest of my Ph.D. committees helped me immensely through this whole process, every single one of you. Stephanie, you've been there in our group meetings for so many years already and have provided invaluable feedback about the MJO and some of the SLIM stuff. And same to you, Dan. You've helped me so much with the linear inverse model, which is not an easy thing. And then Michael, thank you so much for all of your feedback and all of your help in group meetings and just having your door always open. And then Christian Grims, who's logging in close to midnight right now. He's in Germany right now. Thank you so much for all the opportunities you've given me. I'm so excited to work with you too. The AOS department staff, past and present, thank you everyone. Sue and Dee, and all of you have been so helpful. And then Pete, you've been helpful all the way from when I was an undergraduate too, and from TA to my own research. Thank you so much. AOS friends, past and present. I started here. Kyle, you've made it here. You've been helpful in helping me understand EOF analysis in my first year. Zach and Kyle, or I just said you, sorry. And then Luke and Alex and currently Juliet and Zoe, and I just can't name everybody, but my current friends here that have been my friends in Madison for so long, I thank you so much. Lizzie, you're here too, and Elaine, thank you so much for coming. And then my own family, my parents have provided the best support I could ask for, and just have been there for me through everything. And my sister and my brother and his husband, thank you so much. And then I want to give a special thanks to Melissa Breeden, who she was in John's research group too, and I've been working with her. I've just been keeping in contact with her, and she's just helped me so much, and has been a great friend, and also just a great person to look up to in my research, helping me with the limb and everything. And then my partner, Mike, thank you so much for dealing with everything, especially over these last few months. And then also my dog, Odie. I don't know. I would be so much more stressed out without him. So thank you, everyone, and I'd be happy to take any questions.
We'd like to first entertain questions from any students who are interested in asking Maria questions. Zoe.
I may have missed it, and I don't know much about the limb, but the EOS you're using to initialize that, does that contain information about the different teleconnections?
So, yeah, the kind of like, I'm just going to go back to, yeah, it depends what you have in your state vector here. So I have, because I have the zonal lens, heat source, stream function at upper and lower levels. This will have some of these teleconnections like ENSO or MJO. And when I actually look at the optimal precursors for like node 12, I see this pattern that looks like combined MJO and ENSO. So these do have some of those I can create.
Any other questions from
There's a question online too. When you get a chance.
Oh, okay. Yes, I can't see who you are.
Yeah, I was wondering what the significance threshold was on your persistence like charts, especially the permutation.
Yeah, I did a 95% significance threshold.
Okay, because it seems to me like if you did 95% and you had 144 tests, then you're going to have like 6 or 7, right, that are be false positive or false negative.
Mm.
And that was like close to the numbers you had. So I was wondering if you accounted for that.
Yeah, so what I did for the significance testing is I did like a Monte Carlo method where I sampled 100 days and I did that 100,000 times. So that was the method I used for the statistical significance. But you could look at a different method and see how those change.
Can we go to Terry first and then Noel and then Matt?
Yeah, so can we go back to the EOF functions where you had all those, it was like the scatter plots and then you had
Oh,
the dots
sure,
in the
yeah.
middle? And then, yeah, so basically, and then you have that, and then you have all your psalms, and like, I don't know, I'm not a dynamics person, but to me it kind of looks like the dots are like kind of propagating from like left to right in each panel. And I was wondering, do 1 through 4, 5 through 8, 9 through 12 go together? And also, is the way that you categorize your psalms, is it basically the different geographic positions and intensities of the high and low pressure systems over the Pacific? Or
Yes,
how does that work?
so the psalms is, I just used 250 hectopascal zonal winds to do the psalms. And then what you're seeing, so for like, kind of, it looks like it's propagating or something, because we can see that, let's maybe look at this side here. Compare, look at. So for 5, that kind of looks like the leading EOF or that retraction. And we can see that that's clustering nearly along that minus x-axis. And then 1 is a little bit further forward, and we can see that if we look back, our positive anomaly here is a bit forward, but we still have this retraction kind of in that jet exit region. And then whereas 9, you have this retraction that's really strong, but you also, it's picking up on this equatorward component in the projection onto the EOF base space. So it's what's being picked up are those EOF patterns that, here, I can initially show you like here, and then it's kind of showing almost like these linear combinations that you're seeing, but what looks like it's like moving throughout the EOF PC space.
Yeah, and I guess like, how did you define what the difference were between 2 related psalm functions?
So I don't define, it's like an unsupervised, it's an unsupervised neural network that you put it in, and then it is the one, the psalm is like define that. So I'm not prescribing any patterns. It starts with some generalized set of patterns, which I'm first giving it the leading EOFs to go off of that, and then it trains over many iterations to come up with these patterns.
But the metric of closeness is for mean square error, right?
Yeah.
Yeah, I think that's what he was asking.
Oh, okay, sorry. I misunderstood.
I was just trying to understand.
Noel, and then Matt.
What's your hypothesis for why there's so many transitions happening in the lower rows of your sum compared to the upper rows of your sum?
Yeah, I'm just gonna go to that figure here. I only really saw that at 10 days though, because by the time you got to, I lost my mouse here. By the time you got to like 15 days, you started to see more transitions along the polar deflections. And I initially thought, I don't know why this is going so slow. I initially thought that what I was seeing along the equator where it was kind of this transition from that retracted node 9 into the extended node 8, and I thought that that's what it was showing. But I'm not, like, I haven't tested that at all to see if, like, maybe
Would
that's
it
what's
be,
occurring.
would you have the, like, heating towards the equator and it's slowly propagating equatorward and that
Yeah, so that may be
transfer the
like
energy?
a teleconnection pattern or something
Yeah.
that was associated with that, or like a propagating MJO or something. Yeah.
Thank you.
Matt, thank you for being patient.
Well, I'm just wondering about how to regard depth in general, and I don't know if this is the right question to ask, or if you're thinking about it this way, but, you know, in fluid mechanics, you have fluid being pushed through an orbit, it's ultrated depth, and they say, well, it's unstable, and it'll just by itself kind of break down, and you know, if you have a hose with the water on, it breaks into blocks, and so I'm wondering, is it possible to use your technique to ask the question, what fraction of this variability is due to the jet just kind of being unstable and doing its own thing versus clear interactions with its environment as a causal reason? Is it reasonable to partition like that, or I'm just wondering how you think about it?
Yeah, I mean, it's a hard beast to tackle. I mean, one way is kind of looking at these teleconnections, I think, and seeing how, when you just have one or both, how the jet is behaving with respect to the SOM node here. And that's like one way I've looked at, like, if the jet can be predictable, I guess, in certain, when other teleconnection patterns are going on. But I guess in terms of like overall fraction of what can be tied to that, I mean, I think it's still just kind of tackling, understanding first how all of these different processes are related, and like extratropical versus tropical processes is still something I just feel like we don't have a clear picture of, or are trying to.
And I think if I could just add one thing to that. The probability tables tell you how you got from point A to point B. They don't tell you anything about the path. And so you could go and do that. You could kind of map out every one of the 10-day transitions and see how they group, how do those transition sequences group. And that might start to answer questions like that. How many of these just persist all the way through the 10 days? How many go for about 8 days and then bounce around and get back there on day 10? And they might be different in terms of their interaction between eddies and the environment, as opposed to just the jet itself. So there's more work that can be done from this platform,
Yeah.
I think, that could answer some of those questions. Brad, a couple more questions, friend, and I'll get to Kyle, and then Larissa. Brad.
So you showed that there was a probability of going from a contracted to an extended phase, but not the other way around.
Yeah.
Do you have any interpretation of physically why that's sort of a prediction?
Yeah, that's a question I've been wondering. I've been talking to John about it and Melissa. So, you know, one thought I had is I thought it was possibly picking up kind of this negative PNA pattern to a positive PNA pattern, but I'm not sure why the opposite, you know, wasn't preferred. And I don't know, and you know, my only guess is that perhaps there's like constructive or destructive interference for other teleconnections and other specific, or in other SOM states that where you're not necessarily like seeing it transition to the same node every time. But yeah, my only guess was maybe it had something to do with the PNA pattern. But you know, I also really want to look into the case study of that a little bit more and look at, you know, what's actually causing that retraction to extension, which I just didn't do in my own work, but yeah.
One thing that characterizes the retraction events, because Maria's right, they've been more studied than the extension events, is that it seems to be dominated by high latitude migration of anticyclones, either wave breaking from the west or slight migration from the east and over you know, the northeast Pacific. So maybe their spatial divorce from the tropics is a factor that kind of makes them a little bit less likely. I'm not sure why, but it's interesting to consider that. Yeah, Brad.
I'm just wondering whether it's kind of getting back to Matt's point, maybe that extended phase is unstable and it breaks down and keeps it active.
Yeah, that's another possibility. It's quite distinct, I suppose that's right. Kyle.
Yeah, so you noticed that the Psalm 12 had a distinct tendency to remain in place, and also that it was very likely with the ENSO to be associated with positive ENSO use. How much of that predictability and the stationarity ties to the ENSO longevity versus how much of it is 12 as likely to tend towards a stationary state away from ENSO? Did you do any kind of breakdown of independently seeing how much of it is ENSO predictability versus Psalm 12 predictability?
Yeah, so I haven't like looked, you know, I could look at these probability tables during like, calculate them during ENSO neutral state or something and see how they differ. I didn't do that, but I do think that that persistent is really highly tied to ENSO and NJO actually, especially in the later phases of the NJO. So with those NJO phase diagrams I showed you where I looked at the anomalous occurrence during NJO, I recreated those plots during El Nino as well, and I saw that SOM node 12 is just like, it's kind of off the charts for those anomalous frequencies. So, and when I looked at the optimal precursors of that for the limb, it looked like an NJO, the optimal precursors looked like an NJO and ENSO state. So I think that those two tropical processes together really are responsible for that persistence in node 12. So, yeah.
Yeah, predictable convection.
Yep.
Okay. Larissa?
Yeah, so my question is kind of general. So it seems like you've done a really good job of characterizing the what's happening. Like, what's happening in terms of these transitions, like how predictable they are, stuff like that.
Yeah.
It seems like the why, like you
Yeah.
didn't really have a lot of bullet points about that. And so I'm just curious if you thought about, like, because John mentioned this a little bit, but like what kind of methodologies you could try to use to combine these tools to get at the why in addition to like the what.
Yeah. So one way I thought about, or like an avenue of future work is, and I'm really curious about this asymmetry from the retraction to extension and vice versa. So I wanted to maybe apply something similar, like I know Melissa Breeden, she did this like piecewise tendency diagnosis for retraction events to look at kind of what led to the onset of those. So I think it would be interesting to do that, except for these extended events, where you go from retracted to an extended, and see, what seems to be driving
So like
those.
do a composite of the transitions or something and then
Yeah.
some sort of diagnosis of that composite.
Mm-hmm. Yeah, so that's one thing I thought I could look at. And then another future work, I think, to further kind of understand what's going on with these is look at the limb apart from ENSO and see, how much of these transitions are driven by like ENSO or MJO in a separate sense, because the limb, the way I have it, it doesn't separate between those two processes.
Some of the first you've already done in your dissertation, just couldn't present it in the work today, actually looking at the synoptic evolution of the selected transitions. So there is some sense of what might be driving them already, but it'd be good places to launch more detailed studies.
Yeah, when I did a composite of the node, or of the retraction to an extension, it looked like there wasn't I looked at the tropical heating, and there wasn't any like clear anomalies in that, and it seemed to be driven by a lot of extratropical processes. So I think it'd be interesting to look at that in a different method, like the one Melissa applied.
Any other questions?
There is the one from online.
Oh, yeah.
Karen Ross asks, what will be your research topic in Germany, and do you speak German?
Ich verstehe nur ein bisschen Deutsch. But I'll be using the linear inverse model in Germany to look at the predictability of some of their common weather patterns over there.
Liz, do you have a question?
Sure, I'll ask a question. So this data set goes back to like 1950-ish, and you've got through today. Have you noticed any trends in any of the nodes and their frequencies over time? Because you've been investigating this while we had an externally forced signal at the same time.
Yeah. So I did look to see if there were any trends, and there wasn't anything statistically significant for any of the 12 song nodes over time. But prior to that, I removed like this 21-day running seasonal mean from the data, and I think trends. So yeah.
Any other? Greg?
You can, we've talked about the relationship with ENSOL and MJO and all, but have you looked at the more raw relationship between the velocity potential field in the tropical region, particularly along the equator, and retraction extension mechanism?
Mm-hmm. I haven't looked at that, but that would be a great thing to do as well. Yeah.
Any other questions from the general audience? That means everybody, except me. Sorry. Well, if not, let's give Maria another round of applause.